Welcome to this incredibly nerdy little lecture. Okay, so this x86-64 Linux assembler, I have no right to be teaching such a course. The lecture was called, something by an enthusiastic idiot, and that's all I am. So I've been studying, if you can call it that, assembly for a few weeks. I used to write some back in the day, and I decided to pick it up again just for learning. So don't confuse me with a real developer. Anything I show here may not be standard, maybe the stupidest and slowest ways of doing things, but at least stuff works. So assembly, the problem, why don't we write assembly? We don't write assembly basically because of the first sentence. Everything in assembly, in the language itself, I'm not even talking about compiled, in the language itself that you write into your text editor are entirely specific to the CPU and the operating system and all of the hardware that you're running on. So I could write hello world, the most basic thing I can think of. I could even write something that doesn't even do anything. It just returns to the command line. And that would be specific to my computer. It would be specific to this is the computer I'm doing this on is Linux x86-64. It'll be specific to that. If you're running on Linux ARM or if you're running on Windows x86-64, it just won't work. It's entirely specific to that. Why is that? The operating system is the thing that acts as the guardrails between you and the hardware. It gives access to all the input-output streams, the network, memory, all of this stuff that your program almost certainly needs access to. And that's typically done using syscalls. That's requests to the operating system to do a specific thing, to perform some operation that normally needs hardware or one of these limited resources to do. So for example, printing a string to standard out, you've got to give the operating, so you got to line it all up. You've got to give the operating system the address of the buffer that contains your string. And then you got to tell the operating system, okay, go. Now send this string, print this as an ASCII string, for example, to standard out. But it's got CPU-specific features as well. So each CPU you will get will come with its own instruction set. Of course, things have been extremely standardized along the years, but there will be instructions that move data around or perform arithmetic operations on that data, and there will, in many cases, there is also dedicated floating point instructions. So maybe SIMD that does parallelized floating point directly on the chip. That's all going to be specific to the chip. These things have been standardized. There's x86-64 and there's all these other ones, but you have to know that when you're writing assembly. Data storage is not just done in memory, there's also registers. And typically if you want to work with numbers, if you want to work with data, if you want to do any sort of calculation on data or you want to analyze anything, you have to load that into a register in the CPU. And the registers will typically be the size of the bus, so 64-bit. Architecture will have 64-bit wide registers. This isn't to be confused with the different cache levels in the CPU. There's L1, L2, L3, I think, caches that are, the compiler and the operating system is trying to be clever by loading stuff up into cache that can be fetched very quickly instead of running off to main memory. And that'll be much faster. But the registers are an order or two magnitudes faster even than the cache. And they're specific things where you poke a number into that register, and then you can access it within a clock cycle or two, instead of hundreds of clock cycles for main memory. These registers look like this. So this is the x86-64 ones. So there are 16 different registers, and you can kind of see the inheritance from previous generations. So the 64-bit ones are called RAX, or RAX, people say, RBX, RCX, all the way down to R15. But they weren't always 64-bit before that. We had 32-bit if you go back a decade or two. And then there were EAX. E is for extended. So it was extended from AX, which was the 16-bit CPUs going back even further, which were extended from the A register way back in time into 8-bit ones. And all these still sort of exist. You can reference, if you only need the first 8 bits of the RAX register, you can talk to AL. And that will just load in those 8 bits for you. You don't have to talk to the full 64-bit the whole time. And sometimes that's useful because maybe you're just wanting to do a character comparison, and a character is just an 8-bit thing. These have typical uses that I'll go into as we go through this, but you've got typically arguments can be passed. First argument, second argument, third argument are passed to functions via these different registers. Return values are typically held in racks. This is why, or one of the reasons why C only has one return value. It can't do the trick that Python does, for example, where you can have multiple return values, because it's just you're pointing at a thing in racks. And either that's a number or a character or something that's held in racks, or it's a pointer to an address somewhere. It can only return one thing, and that's just an inheritance from this. So what about an example? So I've talked a lot. What about an example? Can we do something? I mean, what's even before hello world? Can we write something that will just return successfully? Can we do that? So up here, I've got my little directory tree, so you can see that this folder is empty. And the only reason you can see it's empty is because my backup file with all my cheat sheets is a hidden directory. But if I just make an empty file, will that compile? Right? It's an empty assembly file. Will that compile? So if I want to compile this as ELF64, which is the executable format on this box, this is what I'm running on. Arch Linux box x86-64. So if I want to compile to that, I have to use ELF64. It didn't error. Right? I'm going to call that a success. What did it produce? It produced this O file here. So what is that? So it's an ELF64 bit. That's not surprising. Least significant bit, blah, blah, blah. But it's not executable. So there's nothing in there I could actually execute. And I think I can even, if I'm brave enough, I can analyze this. And that's what's in there. Right? Lots and lots of zeros. It doesn't go up to 1000 in the address, because that's where the executable stuff is held. So there's nothing in here I can execute. So I could try linking it. So I want to link this with an output of hello. And I want to link this O file with that output file name. Aha. So here's the first error. It can't find the start symbol. So it can't do anything. It doesn't know where to start. Okay. Let's fix that. That's going to get annoying. Oops. We need a start symbol. We should make it global. I know, so code typically goes in a text section, and that will make it executable. And then I need a start symbol. So I've made it global up here, and then I have it here. And what do we do? What do we want to do with that? Well, what did I say in the little presentation? Let's just return. Okay, let's see if that works. So ELF64, hello dot ASM. No complaints this time. Or no, actually, there were no complaints last time. Let's see about the linking. No complaints. No. What have I got?
True.
Yeah, I got 4.5K. And if I've got a handy dandy little function here that I can explore. So this shows what's in an ELF file. So it's got 4,640 bytes. Okay, very good. One executable segment, and the size of the executable segment is 1 byte. That's all of the executable code in that, and it's 0xC3. So now you know the machine code for return. Right, that's all it does. It just returns, and I was able to compile it. So what happens if I run it? Well, let's see. What do you think is going to happen, right? What's going to happen? Seg fault. The new error. We're making progress. So why did it seg fault? Why did it seg fault? So I'm returning, but what am I returning to? Right. So when you have to return, return is matched with a call. You have to call a function, and then the function does its stuff, and then you return from the calling function. What's the calling function? Nothing. So return, there's no guardrails here. It doesn't check to see if you've called something and then check. No, it'll just run through and call that machine code 0xC3. It returns, it knows where to return to because the call command that should have came before it, the call instruction, put an address on top of the stack and said, go here. But the stack's still there. It's got garbage on it. So it jumped to garbage and it segfaulted as it should. So it did kind of what it should do, but not what we wanted. So instead, we need to tell the operating system that we're done, right? Because this is not returning from a function. This is an end of a process. We need to end the process. So we need to tell the operating system that we're done and that the process should be killed. And to do that, we get into syscalls. So a syscall, like I said at the start, is a way of getting the operating system to do something for you that's in hardware. So, for example, if you wanted to write something, you put this number one into RAX. You put the file descriptor, which will be one for standard out, or if you've got some open file number, it'll be that number. You put that into RDI. The address of the buffer that you want to write into RSI, and the size of the amount of bytes that you want to write into RDX. In this case, we don't want to write anything. We want, oh, this screen's going to get annoying. We want to exit. And exit is all the way down here, number 60. So you put 60, or in hex 3C, into RIX, and you put the error code into RDI. And then you do syscall. So let's do it.
Hang on a second, you already had C3, you already had it on that return.
C3 is return.
Oh, 3C.
Yeah.
Yeah, it mumbles the numbers up now.
Yeah,
But you're
and
missing
this,
the argument.
okay, this is 3C. That's so C3, don't get confused. C3 there is the machine code representation of return. Whereas what I want to do, instead of returning, I want
to exit, which is 3C.
I want to do this.
They just happen to be.
Right.
It happens to be the same thing, because I expected when you first did it that actually it was looking for a data stream of unknown value of stack, because your normal return normally takes a value.
Right. But what it did was it looked at that, saw that garbage and jumped to it. And that was untouchable, unwritable memory. And the operating system slapped us on the wrist and said no.
Yeah.
Whereas what I want to do is I want to put 60 in the racks. I want to put some sort of return code, 42, why not? Error code in there. And then I want to do syscall. And writing all these commands is going to get painful. So I'm going to make a makefile. And a link, and I'm going to get some debugging symbols because I always make mistakes. So this is just doing what I did before, but I just don't want to have to write those commands all the time. Hello.o depends on hello.asm, and I create hello.o before and hello.asm. Can do run as well. I don't know how familiar you are with makefiles, but just if I wanna run, that depends on hello, and hello depends on hello.o, and hello.o depends on that. So it will just fall through the whole chain. So if I make this, it works. And if I do hello, no error. What's the return code? 42.
That's good.
Exactly what we asked for. If I change that to 0, make it a bit more traditional. And I can do this. So here you can, I should have had this running before. If I change this to, for example, 32, which is 20 in hex. You see here, B8 and then 3C, which is 60. So this is saying, this is the move racks command. So racks, read this as racks equals 60. RDI equals 32. It's a 5-byte wide command. This one says move into RDI, and I'm moving 20. And then this 0f05 is syscall. And that's, so now I can exit cleanly. So now I finally got the smallest possible, the smallest sensible executable. Yeah, so find the number of the syscall you want on this table, put this value into racks, put other arguments in the right order into these different registers, and then issue syscall, go, and that's what I've got here. I can. And then it will exit cleanly. How about hello world? Right. So how do we get into hello world? So first we have to prepare the right syscall and to send it the standard out. And we need to be able to store data inside our assembly file. So remember, the write syscall takes the file descriptor and the buffer that you want to write and the number of bytes. So let's do that. The write syscall was 1. Standard out is 1. And what was it? RSI next. And then I need some sort of hello message. And was it RDX next? RDX is next. I need the length of this message. Okay, so this won't compile because it'll complain about those symbols have not been defined.
You need to end each of these instructions with a syscall before you move on to the next.
Yes. Thank you.
That makes slightly more sense, maybe.
Yeah.
Very tight little set of instructions.
What do you mean?
I mean, it's very. You need to be very specific. Everything needs to be in order. You need to finish everything with your syscall, and you move on to the next instruction.
Yes. Yeah.
It grows very large, very fast. Maybe.
It gets very, yes, it does. And if you think about it, imagine if what you wanted to print was held in racks, right?
Mm-hmm.
This first step obliterates that data because you move 1 on top of your data that you want to print. So doing this wouldn't make any sense because now it's obliterated. And you could be pointing to memory address 1, which is a segfault. So you have to do this. But then how do we store data in here? We have a new section. We have a data section. And hello message. I'm going to declare some bytes. DB declare bytes. And hello world. And I can't do \n. It doesn't understand that. So I do 10 because I know that's ASCII code for a new line character. Okay, so I've got that. What about the length of that? Hello message is equal to, that's 12 characters, plus this extra one is 13. Now I can make that. Oh no!
You got colons.
Yep. No. I don't think I need colons here.
I know, because you're not separating multiple lines. Okay, yeah, sorry. Yeah, if you spread down multiple lines, you need colons.
Yep. And here you can see this is expanded now. There's lots more going on in here. You might be able to see the 1 here for this. But this is actually run? What happens if I run hello world? Nice. So now we finally got hello world. 25 minutes. What happens if I change this? What's going to happen?
You need to change that.
Yeah, which is going to get boring fast, right? So I can use this character. This character says this point, this address, wherever the assembler is storing the data on the file, the $sign is that number. It's like saying here. If I do here minus hello message, that's the length in bytes between here and this symbol, which means I can expand that however I want. Did I make that? Make run? Yeah, hello world from ASM. Managed to create a 4 file, that's cool. I don't know how I did that. Okay, but now I can expand this hello world, blah, blah. And I don't have to think about the length anymore. It's just the assembler is calculating it automatically. So that's like a little macro trick. Speaking of macros, good programming, you shouldn't have any magic numbers, and this file is filled with magical numbers. So if we define sys exit being 60 and define sys write as being 1, I can already get rid of 2 of the magical numbers. And this should compile and run. It's just macros, yep. More magical numbers. See, we've got exit success is 0. But we've still got this messy thing here with these sort of 5 lines just to print out a message. I could probably wrap that into a macro. That'll make copy pasting much easier. So I'm going to define a macro called write. It takes 3 inputs. And the first thing it does is move sys write into racks. And then it moves into RDI, whatever the first input is. It moves into RSI, whatever the second one is. And it moves into RDX, whatever the third one is. Oops. And then it calls syscall. So then I should be able to obliterate those 5 lines and just do write in the standard out. Hello, hello. It's exactly the same thing. Let's make this file a little bit less noisier. And CD14D. So understanding this was kind of helped me understand how people actually write code in assembly. It's a lot of include files like this, a lot of fancy macros. Starts to make things look a little bit more like a programming language that you might be used to. And this should still run, yep, and now I can do stupid things like this. And oops, make run. And you see here, this is expanded on the right-hand side because of the copy paste. It's a simple copy paste. Okay, where were we? Slides. So we've learned how to do that. We can exit cleanly, and we can print to standard out. What about this sort of format of just copy pasting things? That's a little clumsy. What you would do if you were using any sort of higher level programming language is that you'd write a loop. But assembly doesn't really have handy dandy little constructs for loops. You have to construct the whole thing yourself with jumps, conditional jumps or unconditional jumps. So this is kind of what it would look like in C. There's lots of ways to write this, of course, but you set you come up with a counter variable. While that variable is less than some number, you do a thing, and then you increment that variable. So let's do the same thing in assembler. So we need a variable. I can't use RAX, RDI, and all of that because that's going to get obliterated by the write call. And there are no guardrails. There's nothing to protect against that. So I'm going to use R15, and I'm going to set that to 0. Then I'm going to print to standard out. And then I'm going to increment R15. And I'm going to compare R15 with 10, whatever number. And if it's less than that, I'm going to jump to loop. And loop is just a handy name. I could call that anything. I could call that dog, whatever. But if after this comparison, if it finds that it's less than that, it'll jump to loop. If it's greater than or equal, it'll fall through here. Let's make that. Oh, I always make that mistake. Put a colon there. Okay, and if I run hello, now it prints hello 10 times. So I've shown that here. I used a different register, but it doesn't matter. I just have to pick any one of those 16 registers. It's not going to be obliterated by any of the code. And that's how you write a loop. Everything is very manual. You have to do everything yourself. There are very few constructs available to you apart from whatever is offered by the CPU, which isn't so much in terms of control flow. The semantics of control flow. No, you've got conditional jumps, and that's about it. You've got conditional moves as well. You've got lots of, but it's based on testing a thing and then making a single action based on that. Yeah, command line arguments. So let's get rid of this loop up here, and make that. And let's work down here in this tab. Okay, so if I run hello now, it'll just print that out once. If I run hello with a whole bunch of command line arguments, it doesn't care about the command line arguments because I'm not doing anything with them. Okay, so but let's see if I'm smart enough to do this. Let's start it in the debugger. Right, so just the standard GNU debugger, and I'm going to break at the start symbol, and then I'm going to run it, and I'm going to run it with ABC and version as the command line input arguments. Blah, blah, blah. Okay, so now it's jumped in there, and you see it's right at the top. It's starting to do that syswrite stuff. So I'm right at the entrance to the code. So where are the command line arguments? The command line arguments are stored in the stack. That's not something determined by the laws of physics or something. That's how Linux works. That's how the Linux calling convention. It takes the command line arguments, whatever you give it, and it pokes them one at a time into the stack. And then at the very top of the stack, it pokes in the number of command line arguments that there are. And it's the same thing in Python. It's got, the number of command line arguments it's the same in most languages, not just Python, but the number of command line arguments it includes the name of the executable. So it's one more than you might expect. So can I print the stack? Let's look at the variable that's sitting on the top of the stack. And it's a pointer. So it's a pointer to some address. Can I use my C skills to dereference that pointer? No, because it's a void pointer. It has no idea what it is. Assembly doesn't have type information. Everything is a void pointer. Doesn't have type information. So I have to tell it first before dereferencing it. I'm going to tell it, you're a pointer to an integer. Now dereference that. And I get 3. Cool, that's the number of command line arguments. So that's equivalent to argc. Okay, so what about the next thing? What about if I go to RSP plus 8 bytes?
Oh yeah, of course. So because you not added after you cast.
Yeah, if I did the cast in a different order, if I rearrange the brackets, it would be +1. Yeah. But I'm doing it +8 because it's a 64-bit machine.
Actually, is it? Do I remember rightly? It is an integer. It's not long int.
It might be long. I might be playing a bit fast and loose.
Just very fast on 64-bit system.
Being a little lucky.
Compiled it as L64.
Yes, so I might have just been lucky there.
But 3's fine because all the rest of it's.
But I know this one is not int. I know it's not int. It's a string.
I know what you're going to try and get, but the +8 might be +16.
No, 8 times 8 is 64. It's 8 on an 8-bit machine.
Yeah.
On a 64-bit machine, it's 8 bytes. If it was a 32-bit machine, it'd be +4.
Yeah.
So if I was doing this 10, 15 years ago, it'd be +4.
Yeah.
So this is a pointer to a string. C doesn't really have strings. C has null terminated strings. So it's basically a pointer to a character. So this is a pointer to a pointer to a character, right? That I have to dereference. So a pointer to a character is written like that,
Yeah.
and a pointer to a pointer to a character is written like that. And if I do that, nice, then I get the top of the stack. 16. This should be, what did I call this with? I call this with ABC version. So this should be ABC, and it is, plus 24 version. And the next one, 0. But are you not a little bit tempted? Why stop there? What's next? What will this do? This going to segfault?
No. The program. Yeah.
It's an environment variables. If I keep going through this, I'll leak all of my personal information, all my environment variables. And this is something that I didn't know existed. This is a capability of C, actually. I didn't know that you could do this. Let me see. If I could write a main function, and normally people do int argc and char star argv, and then do stuff with that. But this is perfectly legal and functional C. And if you do that, you will have access to all of your environment variables from inside C. And I wonder if this is how what library in Python it will be the sys import. If you import sys, then you've got access to argv. I forget it's one of those. And I wonder if this is how it does it. Because it's all just stored in the stack. Anytime you call it, Python will have access to that because Python is an executable that will have all the stack information. And I wonder if that's how it does it. But I could, and I tested it earlier, it looped, I could write a little loop that will just keep incrementing n of p and printing it out until it hits a null pointer and then says, okay, now you're done. But now we see just by dorking around in the debugger how we can access command line arguments. So I was trying to call this and it wasn't doing anything, but maybe I can get access to it from here. So I could pop, I think I've got a description of how this works. Yeah, so the data is passed via the stack. RSP is the number of arguments. I just showed you this. The first argument is +8, the second argument is +16, etc., etc. And the stack is manipulated by popping data off it and pushing data to it. So when you pop data off it, it will return that pointer, that information that's sitting at the top, and it will increment, it'll increase RSP in the appropriate way. And pushing just does the reverse operation. So let's get that information. So let's pop into R9. So this should be argc. And then I pop into R10. This should be argv0. And then what I want to do, sorry. I want to be able to print this. So I want to print the first argument. What do I put in here? How many characters do I want to print from that buffer? I have no idea. Right? It could be anything. It's coming in from the user. So it's arbitrary. So I need to calculate it. So now we're gonna get into writing our first function, stringlen. I'm going to use the same calling convention. Into RDI, there'll be a null terminated string. And RIX will contain the length after. So let's see, how do I do this? So first I want to 0 RIX. You might think I should do that. Actually, typically that's not what people do. RIX contain, who knows what's in RIX? Because I'm going to call this from somewhere in my code. It'll contain whatever garbage is in there. I have to know what's in there. This is going to be the little counter that counts the number of characters in it. People don't do this though. What people do is this. What you'll see compilers do is that. And if you think of an exclusive OR between one thing and itself, all the zeros will match up and give zero, all the ones will match up and give zero. It just totally wipes the bit field. Why do people do that instead of move racks 0? This saves like 2 clock cycles or something.
What is surprising is they still do it, because if you compile with the optimizer, it actually chucks all that through and does it for you.
Yeah.
Even NESAM has an optimizer option.
Oh, I haven't been using the optimizer. I've just been using straight.
But it doesn't help you read new code.
Okay, so I've got 0 in racks. RDI contains the null terminated string, so I could compare whatever is at that address with 0. If it is 0, then I'm done. And I just return. If it's not 0, then I increment racks. Racks equals racks plus 1. Then I increment RDI to point to the next character. And then I unconditionally jump to loop.
Probably. It's bizarre because I would have expected.
There's a mistake in here. It won't compile, but it's not a logical mistake. There might be other logical mistakes that I haven't noticed.
I was thinking about in the increment and then making a jump not equal, because but you can't do. Yeah, you have to do that around. Yeah.
Does loop need a code?
Yes, it does.
Because yeah.
So this racks is equal to 0. I compare whatever character this is like the dereferencing. So I'm going to that memory address and saying, what character do you have? If it's 0, I'm done. And I just return. And then racks holds the length of the string. If it's not 0, then I increment racks, I increment RDI, and I jump to the top of the loop. And I do the comparison again. I think this isn't going to work because of something. Because I've still got that as question marks. 42. Just temporarily. It's not going to compile because in line 21, operation size is not specified. It doesn't know how to do that comparison. What's it comparing to what? Because that's a 64-bit register. It's a 64-bit address. There's a 64-bit number there. How is 0 defined here? Is it 8-bit 0, 16-bit 0? So what I want to do is I want to compare at the byte level. So I just want to compare the byte 0 with the byte of RDI. I guess I could use DIL or something here to get the lower 8 bits, but I think this works. It at least compiles, right? We know if it compiles, it works.
What happens if your RDI is a big number?
Okay, it runs here but for a stupid reason. It runs because I put 42 in there. So what happens if
your RDI is a big number and you're comparing bytes? Does it make a difference?
So RDI will be a big number. It's remember, RDI is the address. The little square brackets mean the thing at that address. The thing at that address should be, because I'm in charge of the code, it should be a string. It should be an ASCII string. If you call this with anything else in there, because there's no type information.
We'll treat it as a string regardless of the hell it's
looking at. It'll just happily compare to 0.
Because there's only memory.
And if it's like FFFFF, like 11111, and the last 8 bits are 0, I think it'll pass that comparison.
Yeah.
I think it'll just say it's at the end of the string.
It's almost impossible not to pass, because there will be a 0 at some point. Or it will go to infinity and loop round until
it'll just go all the way through my rounds. Until it hits a string somewhere.
You just loop over the whole. So the only way it gets locked is if there's no 0 in any of your memory ever.
Yes.
Yes.
Because
if it's top of memory, it's like all over the top. But the operating system will protect you from looking at bits of memory you're not allowed to look at.
Yeah.
So
it'll probably seg.
It'll probably say 4 of those.
But now I have to call that function. So I have to organize it again. I put in the RDI, I'm going to put the thing I just popped. And why didn't I pop in the RDI? You'll see that in a moment. So I put the data in the right place. I call string strlen. I know the write command is immediately going to obliterate racks, so I have to take racks and put it somewhere safe. And then I do that. Okay.
No.
So I organize the input, I call the function, I protect the output, and I call the next macro. And I think this works. So if I call out like that, it prints hello. Yeah, I don't have a loop yet. And also I don't have a new line.
Do you actually need that move? Because the write's a macro, it's
Right, the right macro.
Trash racks before you move the arguments into space. If you'd rewritten the algorithm the other way.
If I wrote, yeah.
Because you actually, the way your moves are arbitrary.
Yes, yes. I could turn that macro upside down.
Yes, and then you've got away with not one.
I could save an instruction, yeah.
If I never talked to assembly programmers, they will do this.
Yeah. I'm going to put a new line. This is a dumb way of doing this, but it's the easiest way I can think of because I'm a dumb person. And I pretend that this is protecting me so that I can go on the Windows that has /rpack/n or something. But it's really just because I'm not a good programmer. So I define new line in here, and new line, and at least now I don't have a loop, but at least things will be on separate lines. Okay, and then I can write a loop. What do I want to do here? I want to decrement R9. If it's 0, I jump to continue, which will be here.
Don't you want the new line stuff inside the right?
Not equal to 0, jump back to the top of your.
Yeah.
Different way of doing. Yeah, if you want.
I'm going to jump to exit here.
Print or print line.
And then if I don't jump to exit,
you're going to jump to.
Then I have to jump unconditionally to the top of the loop, which is here. And now this is no longer this is more like, I don't know, what is that, arg C minus whatever's in R9. I think that makes sense.
Except that you've got 2 loops in this code. I can't remember.
That's a very good point. So I've got this label called dot loop, and I've got this label called dot loop. The dot saves you.
Yeah,
if you disassemble this label is not dot loop, it's strlen dot loop. And this one is underscore start dot loop. The dot allows you to scope it. It's a weak form of scoping. So label, I keep making that mistake. Okay, now it works.
My older sampler, which is 650268000, says I don't like jump 0. I like jump not equal to loop, and then just carry on.
Yeah, that's. I think that's maybe a smarter way to.
I mean, I like that kind of stuff to save 4 bytes on safe.
Jump, not 0. Yeah.
Which is what you want to do.
I think that makes sense.
And you're close enough to that jump that you've not got a problem.
Yeah.
Because jump absolute goes as far as you want. But jump, these local jumps cannot. They are limited in the distance in the code they can move.
Yeah, they can only jump within functions.
No, they can jump. If you have a big function, you are going to hit the 4,000.
Okay,
you're not going past that point.
That's true. Yeah. What I planned to do was to, and I'm not going to write it because this took a little longer than I thought. But if I go into my cheeky little backups directory. So what I've got here is, so if I scroll down here, I've defined a version flag, and I've written a string comparison function. And now you see, just to compare strings. So the first thing I do, ignore these pushes at the top. I move things into various registers I call string length. I swap various registers I call string length again. If the lengths aren't equal, then I've already failed. There's no point. This has a nasty little double loop in it, but that's beside the point. If I've passed this point, now I'm in here. And now I'm just doing character by character comparisons. And you see here, even though I'm moving the character into RDI, I'm doing the comparison with the lower 8 bits. And if they're not the same, I fail. I decrement the string length. And as soon as that gets to 0, if I've got that far, then I've won. Then it's a success. And what this allows me to do is to print out a version string. If I do the comparison, where do I do the comparison? I do the comparison here with the version flag. If they're not equal, then I just echo. But if they are equal, I write the version message, version 0.0.1 or whatever it happens to be. This is sort of giving you a sense of, 96 lines of assembly.
It's not that.
That's including macros, by the way. Or sorry, not including the macros. If I expand the macros, and all it's doing is testing input parameters against a particular string. And if that string is in like this, print something. If it's not, echo it back. Things get very, very wordy very quickly. I think I'm walking past the end of my presentation. Yeah, functions I talked about. We've talked about call and return. Function arguments, how are they passed? Functions, I've come to believe functions just don't exist at the assembly level. Functions isn't something really that CPUs understand. A function call is a fancy jump.
Yeah, but with the idea that you always have a protected stack, so you normally push all the variables, I push the whole of the registers to the stack,
Yeah.
and then I would expect a full pullback afterwards.
Yeah, so, but that's a fancy jump. It's a fancy jump, and it moves a couple of registers to put a new stack into view. Function parameters are certainly not a thing at this level. Function parameters are an agreement. It's purely conventional. Whether you push them via the stack in x86, or you push them via the registers via what we do in x86 64. Just going from 32-bit to 64-bit, we totally changed how we do it. Instead of passing by stack, now we pass by all these registers. And if you've got more than
6.
Or if you've got more than 6.
6 is the limit.
If you get more than 6, then you have to start using the stack.
And that is a big break in speed.
Yeah. And this, by the way, is the Linux syscall convention, which is different from the Linux function call convention. It's different. These if you try to use these registers in this way, for function calls, they're backwards. Some of them are swapped. I think functions are just barely a concept at this level, just barely. So pass via the stack, as Linux does when the executable is called, via registers, or something fancy or something else. And here I copied the syscall way of working, which isn't 100% right. What I haven't covered here is a whole load of stuff. So floating point is amazing in x86 64. It's done in dedicated hardware where you've got 128-bit register. It's 128 bits, and you can have a 128-bit number, or two 64-bit numbers, or four 32-bit numbers, and multiply commands work in parallel on all 4 of those at the same time.
Yeah, but now we're into chip because ASM and Intel do it differently.
Yeah.
And Intel do it on 80-bit. They have an extra accuracy which you can access or not access, because actually it's 80-bit and 160-bit at the floating point hardware. Which means you can get.
I was gonna try for this to try and demonstrate some floating point stuff, and I am not smart enough. I am not smart enough. But there's other nice little functions that I haven't shown here. So I've got, I can write this little zero memory thing. So STOSB stores the value of racks to whatever's pointed to by RDI, and then increments RDI. So it puts let's say a 0 here, and then it moves the pointer. And then if you do rep, rep keeps doing that while RCX climbs down from whatever value down to 0. So if I just organize this properly, if I want to put this first parameter would be the memory location, the pointer, and this would be how many bytes I want to 0. And the 0 is done by this XOR trick again. This one little command will just do that all for me. So there's nice fancy stuff in there that I haven't really talked about. So is this going to load? Please load, thank you. Okay, so someone earlier was asking me, are we going to have assembly in the control room? Is that why I'm doing this? No, dear God, no. Projects should not be done in assembly unless you're really working with hardware that just doesn't have any fun. And even then, there's probably a C compiler for it. That's not the point in this. Dealing with assembly, I wanted to learn. All of these things, if you go from very high languages all the way up to Haskell and all the way down, as low down as C, those are all abstractions on top of things underneath them. And abstractions always leak. You can't get away from the reality that's underneath those abstractions. So I just wanted to learn. So it's a learning exercise. So that little function there, what do you think that compiles to, given what I've just shown you? Or what's it doing? It's taking a number and it's returning a Boolean represented as an integer. Is num plus 1 greater than num?
It returns actually one line, I suspect. I know that you can make it come on and go big, but when you compile that, it actually calculates the whole thing, realizes it's always going to return true, and actually...
But that's the thing, it shouldn't always return true.
Because actually there's a flag to tell you whether you can or cannot assume that.
This was the thing this amazed me. So this is what it compiles to. So this is a bit complicated. So it's pushing RBP, it's protecting RBP. This is the base pointer, and it's just pushing that onto the stack because it's going to pop it at the end of the function. So it's just protecting some data. So that the top and the bottom line there are sort of meaningless. The next one, it's moving the stack pointer into the base pointer. The thing is just protected. Okay, this is just some setup. This is doing the setup of the stack and getting stuff ready. And then it's making space on the stack for this EDI, which is just a number that I passed in. But it doesn't do anything with that. It just returns 1. It just returns 1. And you can see that more clearly if you put just even the most basic level of optimization. All this function does is return 1. Doesn't matter what you pass in there. It just returns 1. That feels wrong to me, because what if it's the highest number represented?
There's a flag that stops that.
And now it compares the input against this, which is 7. So it's 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. It's the highest number representable by an integer, and it compares. If it's not equal to that, it sets it at 1, and then it moves that into the output, and off we go. And that's what I think it should be doing. But it's interesting, it's not what it's doing. But even more interesting, you can now understand that. And if you see that code, you can be as equally surprised as me that it's doing, quote, the wrong thing. Yeah, almost done. So dealing with assembly, I think, makes you concentrate on important things. If you imagine so look how long it took us. We didn't even get to the stage of writing the thing that would test against the version string. I had to use my backup cheat sheet for that. It makes you concentrate on the important stuff. So if you were writing something to parse a whole file, would you write a whole nice JSON parser and make everything nice, or would you just go looking for the string? Right? Down at this sort of level, you just go looking for that one thing. It really makes you focus. But it's for learning. It's not for creating projects, of course. But can you imagine how crazy it would be to write a web server? But could you imagine how crazy it would be if the web server that powered this presentation was written in x86 64 assembly? Because it was. Assembly is not so hard. It's kind of, oops, I clicked the wrong thing. It's kind of crazy to do this. But here is a web server. The web server that's been powering this, by the way, written in pure assembly. A little bit of command line argument parsing at the start in order to understand what folder it should serve. Copying that to the server base, so it applies that to whatever web address people look for. Open a socket. This is all just syscall definitions that I've got in another file. Bind it to port 8080, listen for incoming connections, and then start a server loop. And it's just going round and round and round this loop. When the request comes in, it copies that file name to a particular buffer, and then it tries to serve that buffer. Let's see. Down here you have to. This is what allocating memory looks like. You have to memory map files in, and you have to know the length of the file. So you have to do syscalls to call that, read the file, and then send the file. 325 lines of code. a nice little exercise in nerdery. But it can be done. It shouldn't be done, maybe, but it can be done. One of the trickier things was, so down here you have to send C structures in. So I had to construct my own C structures, and I had to understand the layout of memory to be able to build the C structure up to open up the port on 8080. Yeah, I think I finished a little bit too late.